Yeah.
I have some at the house, and I drink whenever I'm at scotch. So I kind of
Scotch.
have for like over a year.
Yeah, you got a ton of hair on your chest. Scotch.
It doesn't just stop there.
Okay, so we will start with this, that's what we are doing now, this kind of titration. Just that our substance of interest is H+, okay? So for pH meter titration, it belongs to potential metric titration. Okay, so the complete, meaning this is a complete picture, really. You will need 2 electrodes. Now, one is a working electrode. So here we will call this the indication electrode, same as the working electrode. You also need a reference electrode. Okay, so this is as if you have a complete cell, right? So the two combined is going to give you a complete reaction. So this is half and this is half. Although here we are dealing with direct mixing. So there will be a potential for this solution. Okay, so why do you have 2 electrodes? Well, it measures the difference in the potential, right? So the delta E is between what's measured here, which is going to be constant, is a reference electrode, and what's in here, that will measure the potential of this solution. Okay, so it measures the delta E. So now, when you turn on your voltmeter, your pH meter, you're going to measure a potential, right? So this is what is measured in this whole solution. So what is measured is the difference between the 2 electrodes, right? The difference between the electrodes. So difference right there. So the difference between the 2 potentials. Any question with that? Okay, so if you are to calculate for the potential at the working electrode, then of course it's a simple math. Is equal to this plus that, so plus that. So for example, a reference electrode has this constant value, 0.246. So in the future, we will talk about reference electrode. For now, keep this in mind, this is constant. So whatever you measure, you can adjust the meter to cancel away this as if this is 0, so that whatever you measure is whatever is at the indicator electrode. Okay? Then you will say that, well, you have 2 electrodes here, but in our experiments, we have only 1 electrode. So that electrode actually is a combination electrode. It has the reference electrode within the indication electrode, okay? That's why it shows up as just 1. For example, here now, you use a combination electrode, okay? So 1 electrode in solution, you do the titration. So let's say you measure this value versus the reference electrode. So the net, the potential at the indication electrode is actually this value, okay? Although that is what you measure because it's against the reference electrode, okay? But the actual quantity is this number at the working electrode. Okay, then you do the titration, right? So you're going to plot the history of the titration, so you can make a titration plot like this. So it's going to be whatever the potentials measure, versus the volume of the titrant added. Electrostatic attraction. Before I pushed the button, it moved. Three. Stop. The little thing down here now. So I can see.
You skipped it.
That's
That's
right.
fine, you went ahead. Yeah. You should be on slide.
No.
You should be on slide 3.
Farther.
Ah.
God, this is nasty. There's so much writing.
What number was that?
Number 3. You're
Number 3. Only
High
on number
titration acid base with
3.
energy potential. That's gonna be nice. It's gonna get real nice.
This is number 3.
Yes.
Okay, so here's an example of such a titration. So slowly, actually you don't need this, you just write. So draw this picture first, right? So this is your electrode, this is your titrant, and this is your substance of interest. So now this is direct mixing. Keep that in mind whenever direct mixing, the difference in the potential yield 0. So what is that difference in potential? Be careful, it's not between two electrons. It's between the two chemicals here. Previously, the delta E was between the two electrons. And now we're talking about just the working electrode potential. So that working electrode potential is going to be measure the difference between the two chemicals. Okay, keep that in mind, between the two chemicals now. So between this chemical and that chemical, titrant. Okay, so the half reactions describe the possibility for the reaction. So you have the half potential here, the half potential here, then this is what you set up for, whether this reaction will go or not, right? This is what you set up for, then yes, positive, meaning it's going to go, okay? So this is a proof. Okay, so now, instead of tracing for the history, if I ask you to calculate the titration curve for this titration, okay, the calculation will be like this, right? So once you add the titrant, once you add that, then you're going to make a point, a data point. So at any point, this is true, right? Notice at the beginning, for direct mixing, the delta E is always equal to 0. So at any point, doesn't matter, any point there, this is true. Any question with that? This is a very important point. Okay, at equilibrium. Okay, so at any point it's equal to that. So this is the half reaction of that, and this is the half reaction of that chemical. So at any point now, I want to calculate for a particular point. Then how do I calculate? Then here, follow this. Well, there are two ways to calculate, right? At any point, you can calculate the potential based on this guy or based on this guy, the Nernst equation of either one. So now the decision is, whichever one is easier. Okay, whether I calculate based on that is easier or based on that is easier. Now look at the two ways to see which way is easier, right? So the Nernst equation, experimental potential during your titration, right? The potential will change. So it's equal to the Nernst equation like this. So there's a standard potential. Now this ratio is going to change during your titration, right? So ask yourself now, can you see the value here? Can you see the value here? Okay, so that make the calculation easier. So this is just a setup, then we will proceed to let you see which one is easier, okay? So, or you can calculate the potential based on this. Now, also ask yourself the question, do you get this concentration easier or do you get this concentration as well simultaneously, okay? So now, investigate the two possibilities.